Do you know Hamid?
Yeah, you're learning Farsi very well. We know him. I know him.
Personally.
I know him. No, I talked to him in emails multiple times. I'm not in person.
Yes, of course.
Okay. So last talk today is given by Maksym and Fedorchuck from Boston College. They'll be talking about the ability of wave hypersurfaces.
All right, well, thank you very much for the invitation. It's a pleasure to be here. It's the last talk of the day, so I'll try to be gentle, finish on time. Let me start with motivation. Motivating question. And I'll fix notation right away. I'm going to work over DVR. Keep the uniformizer. And K will be the field of fractions. And at some point, I'll specialize to everything over complex numbers. So let's consider a following question. Question 1. Given smooth, proper variety or scheme over K, does there exist a model over R? So does there exist R in respect of R? Well, so it often does. And question 2, is there a distinguished such model? Is there a distinguished model? Right, so maybe I'll require here is not flat and proper. And by distinguished, I would like, well, so for example, XR has nice singularities. It's good singularities. Or X. Now the central fiber is nice. So this is very precise, of course. All right, and now for applications, I explain what I mean by good and nice. And so, well, if I consider a projective realization of xk, say it's embedded in the projective space over our field of fractions, using properties of the Hilbert scheme, I can just complete it. Canonical, so it gives a unique completion. Because the Hilbert scheme of the projective space is proper. But of course, the embedding itself is defined only up to an element of PGL n plus 1. So this is defined up to. And so different such embeddings given by the elements of this group give me different completions. And so to find a distinguished model, we would like to attach maybe a non-negative rational number, which is a completion, and then the best model will be the one that minimizes that number. Having said that, let me now sort of make everything precise. So as I've written here, everything is joint work with Hamid, Ahmadinezhad, and Igor Krylov. From now on, I'm going to abbreviate their names using the first letters as their last name, A and K. And so let me talk about what we call Kollár stability. So the setup for Kollár stability is the following. We'll start with H. This is going to be maybe projective, maybe quasi-projective parameter space. And so the variety xk that we started with, I would like to think of it as a k point of this parameter space. All right, so I want now an algebraic group, so affine algebraic group, acting on H. I want a G-linearized line bundle for this action, and I want a non-zero invariant section of this G-linearized line bundle. All right, so the big picture to keep in mind is H, the Hilbert scheme of a projective space. Like we had here. So subschemes of AN will be points of this Hilbert scheme. G will be simply PGL n plus 1. So this is even reductive affine algebraic group acting on H. In general, we have some tautological line bundles, which are automatically, usually linearized. So I'll construct some of them in the specific examples. And what is this divisor D going to be? Well, it's a Cartier divisor in a Hilbert scheme, so I want to take D to be the discriminant, or the boundary divisor. So this will be maybe not a boundary divisor. Divisor parametrizing singular subschemes. Okay, so this is a picture to keep in mind. All right. So with this setup, I would like to introduce a notion of stability for k points of this parameter space H. So, or more precisely for r points of this space. So let me set H naught. So this is for H upper script O for open. This is going to be the complement of the discriminant divisor. And so we have a definition for an R point. So think of this as a map from delta to H. And remember that, so delta is going to be the spec of my fixed DVR. Say that this point is D-stable if two conditions hold. The first condition is, well, that generic point of delta maps into a non-degenerate locus, non-singular locus of the Hilbert scheme. So i.e., when I pull back this discriminant divisor, D, the boundary divisor, it's non-zero in R. what is the connection to the original picture I drew? Well, if H is a parameter space, say it's the Hilbert scheme, maps from speck of R to the Hilbert scheme correspond to flat families, so it's just families over R, and then all I'm asking the generic point is nice, say smooth. If H superscript 0 parameterizes smooth subspace. So, but the real condition for stability is the next one, number 2. We require that for every other map from delta to H with the generic point isomorphic to the generic point of with the image of the generic point isomorphic to the image of the generic point under F. So I'm going to express this as the condition that just the GK orbits of these K points are equal. So think of this as a different model of the same K variety. We have that the valuation with respect to T, so it's just the order of vanishing of this Cartier divisor at the origin, pullback of D. It's a Cartier divisor supported only at 0. We ask for this to be less or equal than the valuation with respect to T. That's the definition. And so I'm going to express this sometimes by saying that F is a D minimizer. It minimizes the degree of D among all models of the generic point. So again, the condition 1 ensures that this is well defined because we're minimizing a non-negative integer. So the D-stable model always exists. I should write this. So of course, by definition, stable model. So here is a way to think of the stability, which is more numerical and in which the connection with the geometric invariant theory might be more clear. So suppose we have two maps, F and F prime, with F spec of K, F spec of K. So it's in the orbit, there's a GK orbit of F spec of K. And so that this is also being part of this H note. So where rho is an element of GK, then quite simply, there exists an integer such that the Cartier divisor pulled back with D log F is T to that integer. So I'm going to write this integer as mu superscript rho, subscript rho superscript L, where L is our line bottom, times the pullback like this. And so this integer I'm going to call is the Hilbert-Mumford-Kollár index. Of F with respect to rho. So why is it called the Hilbert-Mumford Kollár index? Well, one way to produce a k-point as a group is by a one-parameter subgroup. So suppose rho comes from one-parameter subgroup of G. So the way it works is that we have Gm so Tm. I'm using notation here. It's a parameter in Gm, but it's also the uniformizer. So that induces a canonical point, k point of Gm. Just T goes to T. And if I have one parameter subgroup homomorphism, group homomorphism from Gm to G, I get a k point. So let's call this rho as well. So I use a notation. So suppose our rho comes from the one parameter subgroup, and suppose that F is a constant map. So family is constant, i.e. F of the whole base is just F of 0. So this is a point on H. Well then, this Hilbert-Mumford Kollár index specializes to just the Hilbert-Mumford, the usual Hilbert-Mumford index of F naught with respect to rho. In general, it's a bit more general. This is one situation where it recovers the old notion. Okay, and so, summarizing, this is pretty clear. If F is a D-stable model, if it's a minimizer for the valuation of this divisor, then the Hilbert-Mumford Kollár index has to be always non-positive. Yes.
Can you remind me how this D appeared in the Hilbert-Mumford?
Well, D, that's a great question. Maybe D was a section of L. And so, as the notation suggests, the index doesn't really depend on D, only depends on L. So, for any other G invariant section of L, you're going to get the same number.
But it's not D stable.
That is true.
It doesn't depend on D only in that case.
As long as it doesn't depend on D, as long as it's well defined.
For the number.
And the definition is that the generic point goes outside of support of D. So if you have two invariant divisors and the generic point lives outside of their support, those two indices are the same. So they really depend only on the line point.
I see. The index doesn't depend on D, but the stability depends on.
Yes, that's right.
So
That's a good
if
point.
F is stable, then your thing will have character less than 0.
Right, so numerical criterion I can restate is very simple. So F is D-stable if and only if, again, we want this condition that F of spec of A is not an H naught, and the H and K index I should do this. It's really depending on F. So I'm going to put the dependence back. Apologize. It doesn't depend on F. So here it has a dependence. If this is less or equal to 0 for every, and now, well, in general, we ask that it's less or equal to 0 for every row in GK. But if the group G is reductive, then the Iwahori's theorem tells us that every one parameter subgroup, that every k point of G double coset with respect to subgroup of R points of G, the double coset of that point contains a K point coming from the one parameter subgroup. So in other words, and since the Hilbert-Mumford Kollár index depends on the double coset with respect to the subgroup of R points, we can just say that for every one parameter subgroup rho Gn to G, this is in the case if G is reductive. Which for us will be the case only if the group is PGLN. And there will be groups which are not reductive. So in that case, we'll lose if and only if statement for one parameter subgroups, but we still have a necessary condition. You're destable only if for every one parameter subgroup the Hilbert-Mumford index is positive. All right, so let me give an example where this stability notion first appeared and why. This example is due to Kollár, hence the name for the stability. All right, so this would be the case of hypersurfaces, ordinary hypersurfaces in the projective space. This is up to Kollár. This is his 1997 paper. So let's see. So let's take H. So we want to start with a parameter space. It would be a very simple parameter space. Parameter space of degree D hypersurfaces in Dn-1. Well, there is a group G, of course, which acts is going to be PGLN. All right, there is not much choice for linearized line bundle because there is only one line bundle on H, and PGLN has no character. So just one choice of a line bundle, and the stability is really depends on the range the Picard group spanned by the line bundle. So we have only one notion of stability in this case. What is it going to be our invariant divisor? Well, there is D, it's going to be the discriminant divisor. And its invariant section of some G-linearized line bundle precisely its classical formula for the degree of the divisor is that it's the discriminant of a degree D homogeneous form in n variables, as I think this number is not important, but it exists. And so notice that, of course, H minus the vanishing locus of D parameterizes precisely smooth hypersurfaces. And then what does destability mean for families of hypersurfaces? Try to do it here. So F is destable if, well, first of all, for every choice of coordinates from the projective space, the homogeneous coordinates, and every one parameter subgroup, diagonal, so once we have every one parameter subgroup can be diagonalized in some choice of coordinates. So let's say we have diagonalized our one parameter subgroup. have the following. Well, first of all, we can write f in this chosen coordinates. F is, so it's a family of hypersurfaces over our GDR. So this is coefficient R. Sum of GI is T. And then we always have that. And the d-stability condition is very simple. It's numerical. So we ask that multiplicity with respect to rho of f. And so what is it? What is this? This is going to be simply the valuation with respect to t of the polynomial which you get from f sub t by plugging in that substitution. Change of variables. So we do f sub t, tb1, x1, tbn, xn. This is what the multiplicity is. And it's less or equal to d over n. D is the degree of the hypersurface, n is the number of variables, and times the sum of the weights. And, well, I'll rewrite this as follows, maybe. This is less or equal to 0, because the difference is this index. This is a computation. Yes?
So what you want to take the fibration of something of an element in the DBR, so.
Yeah,
Do you think
well,
so on the backside?
you take the largest power of t that divides the cell.
Yes. It's the valuation with respect to t.
It's a valuation with respect to t. If you want to be, I can do this. It's a maximum n such that that guy lies in the ideal. In the polynomial ring where you have t and xi's. It's also the minimum of the valuations of the monomials that you get by making the substitution.
Nothing to do with this.
Well, it has to do, well, it's a Hilbert-Mumford index with respect to the line bundle, maybe O of 1, on the parameter space, and of course the discriminant is a section of a power of that line bundle. So it does have to do something with discriminant. The point is that discriminant is a PGLN invariant. And so this comes from the PGLN invariance. And so how do we see that? Well, suppose your one parameter subgroup was actually a subgroup of SL, sum of weights is 0, then the discriminant is SL invariant. And from the invariance, how does the discriminant, how does it do when you make the substitution, how does the discriminant change? Well, it changes precisely by scaling t to the power multiplicity. All right, so this is a numerical criterion for stability of families of hypersurfaces, and it can be used to prove some results about such families. So let me give an illustration. And as in GAT, so this is very similar to GAT stability of hypersurfaces, right, with respect to PGLM. As with GAT stability, you can say more about lower degree case. Do explicit description. So the theorem, so I'm going to state this as due to Corti and Kollár. Not in the same paper. Is the following. So this is 96, 97. Suppose R over R, spec of R, is a generically smooth d-stable cubic hypersurface in well, arbitrary number of variables. And of course, again, as we started with, if you have a smooth hypersurface over K, you can always complete it to some cubic hypersurface over R, and then you have a d-stable model by definition. Then, well, first of all,
Can I ask you a
Yeah.
question? So on this Hilbert scheme, in your case, the linear system,
Yeah.
like, if I use the tautological line bundle on that thing,
yes.
its character with respect to the action of PGLN is not exactly this one, is it?
Right.
Hmm.
Well, the PGLN has no characters. Yeah, but this is.
The tautological, not the PGLN, tautological PGLN equivariant or linearized line bundle on the linear system has a character, right? Why are you saying that this is equal to the index? That's what I'm trying to understand. Can I see it through the line bundle character of the GLN, PGLN linearized line bundle? Can I see it that way? Somehow it doesn't quite become D over
You
N.
can't see it from a character, no.
Yeah, okay.
Yeah, if you can, again, you will specialize to the character if you had a hypersurface which was fixed by one Vermeer subgroup and your family was trivial family. So the Hilbert-Mumford index is what you said.
Yeah,
But this is not quite.
not quite.
It's related, but not quite. And so maybe I actually want to sort of to make my statements more precise. Let's just take R to be our series over C. So that I can talk about singularities of threefold. So in this case, XR I can think of as threefold over complex numbers. It's fibers over a curve over my base. And so the XR has at worst couple singularities. The multiplicities are at least 2. So in general, and if n is 4, so we have cubic surfaces, XR has at worst terminal singularities. So we get something which is essentially more fiber space vibration, or fibers are cubic Delphi surfaces. So of course here everywhere I should take n to be at least 4. So interesting stuff starts on those cubic surfaces. And so this is a birational geometry statement. And 2, the central fiber x naught is integral. So what this result says is that if you have a smooth cubic surface of a refraction field of a smooth curve over complex numbers, you can find its model over the curve where all the fibers are integral and the total space has at worst terminal singularities. And of course it's Gorenstein because it's a hypersurface. All right, so this is something that we're going to be looking to generalize. Let me spend maybe a few minutes on working out this. That was indicating where this comes from. So let's do sketch proof, at least for parts of the statement. So integrality of fibers is probably the easiest. So suppose x naught is not integral. So you have a cubic hypersurface. The only way it's not integral, where you can split off a linear component. It's the easiest. Then the family of cubics looks as follows. So you split off a linear component, you have and then you have plus t. Okay, so let's take rho of t act on our variables. So f is a cubic, g is a quadratic, h is a cubic. Let's act on this first component with weight 1 and all other components with weight 0. And let's compute the multiplicity. So what is the multiplicity of f? So this is evaluation with respect to t. After I make a substitution, I get this expression. So this is at least 1. If I have a power of t. And so this is, of course, greater than degree 3 over n times 1. So we get unstable. So unstable. We get an unstable family. And so a stable family cannot have a non-integral central fiber. And I'm not going to prove terminality, but the double points is again is easy to see. Let's take another one parameter subgroup. So let me take T to be a point in the central fiber. So now I'm specializing to n equals 4. Yeah, I'm not. So I'm just doing double points. So let's take this point in the central fiber. And I want to show that my total family has, of course, double singularity, multiplicity of 2 singularity at this point. Let's take rho of t to act with weight 1 on everything except the last coordinate. And then stability implies that multiplicity with respect to rho of should be less or equal than 3 over n times n minus 1. So it should really be less or equal than 2. And if you dehomogenize with setting xn equals 1, you get precisely the local equation of the point P in the total space. And the multiplicity condition says that the tangent conc has multiplicity 2, has degree 2. All right, so that's the idea. You have to do more work for terminality, but what you actually prove is that the singularities of cubic surface fibrations are compound duval. So you can find a hypersurface sections for every point with at worst duval singularities, and you use a recognition. You use standard forms for duval singularities to do that, plus the numerical criteria. Okay, so how do we generalize this? I want to define stability for weighted hypersurfaces, and our motivation is for doing this. So why? Is the study of Del-Pezzo fibrations of low degree. So these are more fiber spaces of threefold over a curve, where the relative canonical divisor is anti-ample, the total space is terminal q factorial, relative Picard number 1. So this is one of the endpoints of MMP, and so by classification of the endpoints of MMP for threefolds, one of the possibilities is that you get a Del-Pezzo fibration. And we can think of a Del-Pezzo fibration, so it's a family of Del-Pezzos over a curve. And if I have a smooth del Pezzo over a function field of a curve, so del Pezzo of degree a squared less or equal to 3, then every such del Pezzo can be realized as a weighted hypersurface in a weighted projective space. So it's for degree 3, we've already seen it sits in P3. So, over K. P2, 1, 1, 1 over K, so this is degree 2. P3, 2, 1, 1. This is K squared equals 1, K squared equals 2, and K squared equals 3. And this sits as degree. 3 respectively, 4 respectively, 6 weighted hypersurface. So if we define a notion of stability for weighted hypersurfaces, in particular, we'll obtain a notion of stability for the low degree del Pezzo fibrations of respect of our DVR. But I want to do this, I want to work more generally, so let's say I'm going to work over C from now on. We have a graded ring. So it's graded with weights of the variables given by integer CIs, such that we have S weights which are greater than 1, and they are co-prime. So why do I want this then? I have weighted projective space B, so this is just project S. And it has only isolated singularities. So it has isolated singularities. And in particular, a generic Cartier divisor on such a weighted projective space is going to be smooth. And I really like my generic fibers to be smooth in order to run the machinery of D-stability. Okay, and so what is this isolated singularities? So they're V1 through Vs, where Vi is the point. This is ith place. Of course, projective spaces have no singularities. P2, 1, 1, 1 is a cone of a Veronese in P5. So it has this cyclic quotient singularities at the vertex. P3, 2, 1, 1 has two isolated cyclic quotient singularities and so on. I want to study hypersurfaces, weighted hypersurfaces, so let H be a linear system of degree D hypersurfaces where the product of the weights CIs divides D. So this ensures that this is the line bundle divisor of this linear system is Cartier. My G will be automorphism group of P. And notice that on the G linearize a line bundle, well, we first pick a line bundle, there is only one, but the group G has S characters. And G has S characters. So we have S plus 1 possible choices for the line bundle, where S is the number of singularities as a weighted projective space.
In the previous example, what was the statement that showed you your hypersurface has only isolated singularity?
Uh,
The one that you showed the double point singularity.
For cubics?
Yeah.
Fibrations, surface fibrations?
Yeah.
Well, I haven't
But there is
done
some.
this, but there is something. A terminal implies isolated. So you prove them.
That was the condition.
But yes, in particular, you have to check that they're isolated.
Yeah.
And there is some work to do. If you take a random d-stability notion, then the singularities don't have to be isolated. But for cubic fibrations, cubic surface fibrations over a curve, they are. And for some of the things we're going to do, they are as well. So now, to have d-stability, I need a line bundle and a section. So I need an effective G-invariant Cartier divisor, and we're lucky because there are exactly S plus 1 G-invariant boundary divisors on H. So what are they? Well, we have the usual divisor. So we take a hypersurface in H where X has ordinary double point at a smooth point of weighted projective space. And we take the closure of such things. That's a discriminant. And then for I equals from 1 to S, we have boundary divisor. Let me call this script delta i's. X and H, such that X passes through the singularity VI of the weighted projective space. And so now, every effective combination of those boundary divisors defines d-stability. D-stability. Because it defines, so you just take L to be of D and it has a unique linearization for which D is going to be invariant divisor with respect to that linearization. And so we can ask, well, what can we say about D-stable families of hypersurfaces? Let me explain a key proposition. I got some numerical criteria. Which tells you how to compute Hilbert-Moffat Kollár indices of families with respect to this divisor D. So suppose I have a family as before. So now this is weighted degree D hypersurface over R. Generically, and rho of T is a one-term or subgroup that acts diagonally on our variables. Then we can compute the Hilbert-Moffat indices of the family with respect to these boundary divisors, and in particular for every D, because the Hilbert-Moffat Kollár index is additive in the line bundle variable. We can compute Hilbert-Moffat Kollár indices for every effective line bundle. So if I do delta I, this is going to be multiplicity that we've defined before, minus, this is a very simple formula, D is the degree of the hypersurface, Ci respective weight is a variable with respect to which delta I is defined, so di. And then for the discriminant of delta naught, this is more complicated. It's going to be, but again, it's expressed in terms of the multiplicity and the weights of the action of the one-parameter subgroup. So minus the sum, L from 1 to n. This is somewhat similar. We have d over CL, L, dl. So I have a completely numerical way of, for example, proving that certain equations are unstable. And let me just say what those MIs are. So ML, so this is for all equals 1 to n. This is a number of monomials in our graded ring S in degree divisible by x, L, you can see minus 1. So this is something computable, but not by any j. And so maybe if you've seen Macaulay's computation of a discriminant of a homogeneous form, this comes from that. Where we're computing a degree of a semi-invariant given by some discriminant, or as a resultant of a quasi-homogeneous polynomial, and this numbers ML pop out. So now it's a sum. All right, so maybe I'll do an example with this definition. And so in particular, I mean, there are some things that we can do with this. First of all, we have a notion of stability. There exists D balanced, so effective G invariant divisor such that D stable families must satisfy multiplicity with respect to rho is at most d of the sum of the weights of the weighted projective space times sum of the weights of the one-parameter subgroup. So in this d-stability condition, the weights of the one-parameter subgroups plays the same role. Hence the name for balanced. And we actually use this stability to construct some nice models of degree 1 and 2 Del-Pezzo fibrations. Right, and to illustrate what we can do, so this is, I mean, we're writing this up as I'm speaking. The first theorem is the following. So let's take, let's specialize to the case where H is a parameter space of degree 6 hypersurfaces in this weighted projective space. So this is a degree 1 Del-Pezzos. We have 3 boundary divisors in this space, delta naught, delta 1, delta 2. And so if I take a particular linear combination that I'm going to call Igor, and this is going to be epsilon delta naught plus delta 1 plus delta 2. So epsilon here is very small, but positive. And generically smooth, so a Igor stable family so this is going to be F delta into H, and so this is just degree 1 Del-Pezzo over R. model of a degree 1 Delpets over K satisfies. So we can also think of this as XR with respect to R. Satisfies three conditions. First, the total space XR has Gorenstein and canonical singularities. In particular, all fibers avoid the cyclic quotient singularities as a weighted projective space. And two, the central fiber X naught is integral. So we establish a result in birational geometry using this without doing any birational geometry and simply knowing the classification of threefold canonical singularities, which are again confounded all singularities, possibly non-isolated. And well, of course, the result itself for families, so existence of such canonical and Gorenstein models of Delpets fibrations was known before by work of Alexeyev, 14, in the invariant case, G-invariant case under the, well, in the case of finite group action, and the equivariant case was known, this is the work of Loganov from 2017, Alexeyev and 14 were 1990s. So, as I said, we don't do any birational geometry to get this result. At least not any hard geometry. But if we do a little bit more work, that goes, so by going outside, slightly outside of the setup of my talk, so not working just with weighted hypersurfaces, but with slightly worse degenerations of those hypersurfaces, we can prove that, I'm just going to say phrase it like this, debalanced, stable families of degree 1 Delpets fibrations This is XR with respect of R. So now, debalanced stability here is with respect to the line bundles that I wrote, but on a slightly larger space, satisfy better conditions. The total space XR is terminal and 6 Gorenstein. So you lose Gorensteinus, but you gain terminality, which are isolated compound of all singularities. And X naught, the central fiber is integral. So this proves the conjecture of Forte about existence of such models from his 96 paper, basically. He had this result for degree greater than 2 Delpets fibrations. Degree 1 is the most difficult case, and we can do it by running a correct, finding a correct divisor and running the notion of the stability machinery on it. All right, well, I'll stop here.
Any questions or comments?
Is there some notion of d-stability that tells about singularity type of higher dimensional singular set?
You mean what
And we don't have basically these non-isolated cases.
But you want the basis to occur? I mean, again, you have this numerical stability, and then you can read off some things in some situations. In general, it's as difficult as any JT problem. You can classify non-isolated singularities when degree is low enough. geometry is very large or not.
Any other questions? Or? So let's thank Maksym again. Then tomorrow, that's from 9 again. No, it was scheduled.